Chapter 3 Design Fundamentals and Mass Conservation Equation for Ideal Reactors. The first part of this chapter presents a qualitative discussion of reactor design questions that the chemical engineer must answer before proposing equipment and operating condition. Following this, the fundamental concept of reactor design is introduced. This is the use of conservation principle to predict reactor performance. In this chapter, the quantitative treatment is limited to isothermal operation of the two ideal reactor types, stirred tank and plug flow. Although illustration of deviation from the ideal types are discussed in section 3.5. The mass balance is the only conservation principle required. Multiple reaction, multiple reactor and variation in operating condition are presented in chapter 4. Still, for the ideal reactor types and for isothermal condition, then in chapter 5 quantitative treatment for non-isothermal reactors is considered. This requires application of the conservation of energy principle as well as that of mass. Since non-isothermal conditions are common in flow reactors, some general discussion of temperature effect is given in the last part of this chapter, section 3.7, in order that we not give the impression that reactor performance can be predicted using only mass conservation equation. Will the illustration in chapter 3 to 5 are for homogeneous reaction, the form of the conservation equation is generally applicable. Hence, in the latter chapter, where heterogeneous systems are considered, we will frequently refer back to the equation in chapter 3 to 5. The mass conservation equation includes a term involving the rate of reaction. This rate is the same property of the system as that defined in chapter 2. In fact, for a well-mixed batch reactors operating at constant volume, the conservation equation reduces to exactly the same expression relating concentration to the rate as that given in chapter 2, equation 2.1. For other reactor types and operating condition, we will see that the rate is related in a different way to concentration in the reactor. 3.1 Reactor design. The first discussion that must be made in design are to choose the type of reactor and method of operation. Common types and operating methods for reactors were discussed in section 1.5. Classification of reactors. The next step is to evaluate the reactor performance, that is, the reactor size, composition of the product, steam, and the required operating conditions. The latter include temperatures, pressures, and composition within the reactors. The first discussion may not be possible without carrying out the performance calculation for several types of reactors. Ultimately, the choice of reactor would be made on the basis of profit, safety, and environmental factors. The kind of reaction system may be a primary factor in determining the type of reactor and method of operation. For example, batch operated tank reactors would not be used normally for gas phase reactions because the production rate of product would be uneconomically low. In contrast, such reactors may be well suited for liquid phase reaction involving expensive materials. Example, pharmaceutical industry, and where careful control of condition is more important than labor cost. The data that are available usually consist of the temperature, pressure and composition and flow rates of the feed streams or initial charge for a batch reactor. This information along with the required production rate of desired products constitutes the design condition. With this data and the proposed type of reactor and method of operation, reactor performance can be evaluated for the ideal reactors considered in this chapter. The evaluation requires only solution of the mass conservation equation. There can be many combinations of size and operating condition for a given reactor type which satisfies the design condition. The optimum design from a profit standpoint depends on raw materials, initial and operating cost, and the market value of the end products. First, the method of calculating reactor performance needs to be established and then an optimization technique used to find the most profitable design. Generally, some of the conditions such as feed composition will change with time. Such change may be abrupt as in switching to feed that contains material of a different composition, or they may be mild cycle change. The problem in reactor control is determining how to change operating condition so that the reactor returns to optimum performance as quickly as possible. First, a specific operating condition must be chosen to use as control points. Then a policy or strategy is developed for responding to fluctuation in such a way as to maximize profit. The resulting control procedure may be manual. Alternately, it may be a semi-computerized procedure in which a computer is used to determine rapidly the value of the profit function, but the indicate change in operating condition are made manually. Finally, it may be possible to employ a direct digital or closed loop procedure in which adjustment to operating condition are made automatically on signal from the computer. All control procedures to be successful require a knowledge of how to design the reactor for a set of constant design conditions.